We have been focused on proving theorems for a number of lessons now, but it's not the case that every statement is true. In fact, many statements are false. And so the skill of disproving a false statement, this is an important one, and this is the focus of this lesson. And we will focus on disproving universal statements. So to disprove a false statement of the form say for all y in some set S of y. Well, let's think for a moment how we would do this. If it's not the case that S of y is true for every y, then there is at least one y such that S of y is false. And this is what we will do. We will find what's called a counterexample. And a counterexample is a specific, well, it would be a specific y value in this case with S of y false. And then if you give this y and justify why S of y is false, you have therefore disproved the statement for all y S of y. And this is the goal of today. How today will go is we will start off with a number of statements that I tell you are false and justify that with counterexamples. But then we will do a few where I say prove or disprove. So we will have to think, is the statement true? If so, prove it. And if not, give a counterexample. Here are our first two examples. Let's start with this one over here. It says for all prime numbers p and q, p plus q is composite. This is a universal statement and it's also false. So let's give a counterexample. I need to find two prime numbers, p and q, such that, well, p plus q is prime. And this is not too terribly difficult to think about. We can just take, for instance, p is 2, and then we can take q is 3. Then both p and q are prime, and their sum is 2 plus 3, which is 5, and this is also prime. The definition of composite integer or number is an integer bigger than 1 that is not prime. And so in particular, 5 is not composite. And this completes this counterexample. Now for this statement, for x, y, z integers, if x divides y times z, then x divides y or x divides z. This again is universal, but it's an implication. So we have a little bit more to think about. Moreover, this side of the implication, the q part of p implies q, is an or. So we have to be careful when we think about what would a counterexample be. In order to disprove this, we need a specific x, y, z, such that we want p to be true and we want q to be false, right? Because p and not q is the negation of a p implies q. So we have to think a little more, I think, than the other one. And sometimes coming up with a counterexample, you might have to try a few. So let's try here 10, y is 5, and z is 4. Okay, these are definitely integers. Then x divides yz as, well, 10 divides 20, which is 5 times 4. However, now, if Q is false, and this goes back to De Morgan's, we would need X does not divide Y and X does not divide Z. X does not divide Y as 10 does not divide 5, and X does not divide Z as 10 does not divide 4. And this is now a justified counterexample which disproves this statement. Here are our next two examples, and they both come from sets. First, we will disprove for A and B finite sets the cardinality of A minus B equals the cardinality of A minus the cardinality of B. So let's just take maybe A and B to be the same cardinality. I will make A, B, 1, 2, 3, and B, B, say 4, 5, 6. I could create other examples, but we only need one here in order to disprove this statement. Then A minus B is A. So the cardinality of A minus B is 3, and the other side of the equation is 3 minus 3, which is 0. 3 is definitely not equal to 0, and so we have a counterexample. Now, this statement over here about sets is actually quite similar, at least my thought process about it is, but this says if C is A union B, then A equals C minus B. Certainly I don't want to use this A and this B, because if I took their union and then I subtracted B, I would in fact get that A. So this is kind of a neat example on the left-hand side. For that example, this statement is true, but it's not true in general. So I will just edit this slightly. Let's let A be the same, 1, 2, 3. And let's let B be equal to A, 1, 2, 3. And then this C here, which is A union B, is 1, 2, 3. However, C minus B is the empty set, and this is not equal to A. So this is just one counterexample to that statement. My next two examples of disproving false statements involve the floor function. This is a function you may have seen in a math course or a computer science course, and we will see again later in the semester in our functions lessons. But if you take a real number, the floor of x is the greatest integer less than or equal to x. You can think round down. So the floor of 3.1 is 3, but the floor of 3 is also 3 because 3 is an integer. Now we want to disprove these two statements about the floor function. And the first is here. This says for all real numbers, the floor of x minus y equals the floor of x minus the floor of y. So here, let's take x is 1.2, y is 0.8. Then maybe I'll compute the right-hand side first. The floor of x is 1. The floor of y is 0. And so the floor of x minus the floor of y is 1 minus 0, which is 1. Now, on the other hand, x minus y is 1.2 minus 0.8, which is 0.4. And the floor of x minus y is the floor of 0.4, which is 0. And you see 0 is not equal to 1. So we have a counterexample to this statement. And you see, justified. Every counterexample must be justified. I wouldn't just say let x is 1.2, y is 0.8 and walk away. We must justify everything we do in this course, really. right, well, here is the next one. We could think, what happens if we use the same example? Will we get a counterexample? If we had 1.2 and 0.8 multiply, we get 0.96. So this side, when we take the floor, we would have 0. And on this side, we would have 1 times 0. So we have 0. So we do not want to use the same example. So let's think of something different. Let's take x is 8.8, y is 5. Then the floor of x is 8. Y is an integer. The floor of y is 5. And I chose these so that x times y is also an integer. If we multiply, we get 8.8 times 5, and this gives us 44. So the floor of xy is 44. But if you multiply these two, the floor of x times the floor of y, we just get 8 times 5, which is 40. And this is definitely not equal to 44. And so here is a counterexample to this statement. Now, of course, just as a comment, many counterexamples are possible for both of these statements. This will be my last example where the instructions say disprove, and then we will see a few where I say prove or disprove. This is a great example, and it has to do with power set. We have A, B finite sets, and then the statement says that the power set of A union the power set of B equals the power set of A union B. And I'm telling you in advance, this is false. We just need a specific counterexample. This illustrates that a simple example can be a wonderful counterexample. And quite often, a simple example can really make you understand why something is false or true, rather than building some super complicated example that not only takes a lot of time to think up, but also might be difficult to even process. So let's take the simplest possible example I could imagine. Maybe not using the empty set, but the next simplest example I can imagine, and that is where A and B have both just one element. And let's see what happens. So let's let A be the set containing 1 and B be the set containing 2. Okay, I can write out this because this will have the empty set and the set containing 1. And I can write out this. The power set of B is the empty set and the set containing 2. So what is this union? The power set of A union the power set of B. Well, we notice it has 3 elements. It has the empty set, the set containing 1, and the set containing 2. Now, I don't even need to write the full power set of A union B, although I could. But if we notice, A union B has 2 elements. And so the power set of A union B has 2 to the 2, or 4 elements. But on this side, that only has 3, so it cannot be equal. So we have our counterexample. In fact, if we actually write the elements out, the power set of A union B has 1 more element. It has the element containing 1, 2, right? But it's fine. This is justified counterexample. Now, prove or disprove. The sum of 3 consecutive integers is even. When we have this choice of prove or disprove, you might not know which way to go about it first. You could try to prove it, and that is not necessarily a bad way to start. So let's just strategize what would go through our head if we tried to prove. Well, I have 3 consecutive integers, right? And I am working generally, because that is, if I was going to prove, I would have to work generally like this, where I have 1, 2, 3 consecutive integers, add them up. You notice here I get 3x plus 3, which, let's see, is that even or odd? Really, it could be either. If you tried to break off a 1, we would have a 3x plus 2 plus 1, and then this thing could either be even or odd. It really just depends on the integer x. So that makes me think that maybe proving is not the right technique, and in fact, we do want to disprove this statement. If we go back to our idea that simple examples are wonderful examples, you could try to come up with something. Try 1 plus 2 plus 3. Okay, this is even. This is not a counterexample, so let's erase this. Did not work. Okay, well, let's just back up 1. Okay, this is odd. You see, now we have a counterexample. So I would just say notice to make this into a justified counterexample. 0, 1, 2 are consecutive integers. And then I can add this. 0 plus 1 plus 2 is 3. And comma, 3 is odd. Maybe I'll add the word where. And this part here would be my fully justified counterexample disproving this statement. Here are my next 2 examples, and they both have to do with subset, and this is very similar to something that we did in the very last lesson, which was our set theoretic proofs day. We have A, which is integers x, such that 15 divides x. We have set B, which is integers x, such that x can be written as 25m minus 10n for some integers m and n. And then we want to prove or disprove. A is a subset of B, and prove or disprove. B is a subset of A. I like this example very much, but in any case, one of them I will tell you is prove, one of them is disprove. So in particular, we do not have A equals B here, but let's figure out which. Let's see. I will prove A is a subset of B, and I will disprove B is a subset of A. Let's let X in A. Then there exists Y and Z. Well, we know 15 divides X with 15Y equals X. Now, just like the example we did in the last lesson, I want to write X as 25 times some integer minus 10 times some integer. And I can do that here. Then X equals, well, it's 15y, which is 25y minus 10y, comma, and as y is an integer, we see X is an element of B. And so this completes this direction, just proving that A is a subset of B. Now, I mentioned B is not a subset of A. How do you prove this is not the case? Well, I need to find one element in B that is not in A. This is how you disprove that B is a subset of A. Okay, so I'll just make this observation. Notice 10 is in B as, well, I need to generate 2 integers, m and n, such that 10 is 25m minus 10n, n. So as, let's say 0, -1 are integers, and 10 is 25 times 0 minus 10 times -1. Okay, so that justifies that 10 is in B. However, 10 is not an A, as 15 does not divide 10. So therefore, B is not a subset of A. And this is our counterexample that disproves this. I will end today with 2 examples that read prove or disprove. I will just tell you we will prove them both, but they read a little bit different than many we have looked at today. In fact, both of the statements are there exists statements. So when I prove each of these, proving a there exists, it's the same technique or the same idea really as disproving a for all, because to prove these 2 statements, I need just one example. And this will prove, right? Proving a there exists means generating an example. So that's what I need to prove these. I need one example of, for this one, a real number, x, such that x is bigger than x squared. And then, well, I will discuss the other one when we get to it. So let's do this first. Find one real number x, such that x is bigger than x squared. Let's let x equal 1/2. Then x squared is 1/2 squared, which is 1/4, and 1/2 is bigger than 1/4, which means x is bigger than x squared. And we have proved this, because, like I said, the statement was a there exists. Now, let's prove this. Again, generate an example. The statement is there exists an integer that is a perfect cube. So this means it is the cube of an integer. And x plus 1, the very next integer, is a perfect square. And this means it is the square of an integer. Let x equal 8. Well, 8 is 2 cubed, which means that x is a perfect cube. Now, x plus 1 is 9. And, well, 3 is an integer with 3 cubed is, 3 squared is 9. And so this means that x plus 1 is a perfect square. And this is the end of this proof. It was an existence type proof.